All right, so because it's a little more complicated, I want to get the ionic formula naming scheme out of the way first. So the first thing, obviously, is you want to be sure that you know that it is in fact an ionic compound. And the simple answer here is, well, is it made of ions? And then if the answer is yes, then it is in fact an ionic compound. But first off, let's just say that you're going to look for a metal-nonmetal pairing. And then the next thing that you need to be able to do, we're going to be talking about a couple of things in this unit, namely formulas and names that go along with them. So the first thing you need to do is to figure out what the empirical formula of the ionic compound is. Now, we talked about this a unit or two back when we talked about compounds in general, and that the whole idea is that they had a consistent ratio of ions to the other ions, and that ratio is whatever it was that actually kept the entire thing electrically neutral. Nature does not like excess charge. So, for example, we talked about table salt back then. And so sodium has a +1 charge when it is an ion. When chlorine is an ion, it adopts a -1 charge. Again, these are elements that are at the far end of the periodic table, at the far edges, so their charges can be deduced from what column they are in. And for the charges to cancel each other out, they have to be present in a 1-to-1 ratio. One positive, +1 and -1 adds up to 0, and we're good. All right, so the ionic or the empirical formula for this is NaCl. When the superscript should be 1, we omit it. Okay. Now, a quick trick here. Whenever the charge on the anion and the cation are the same, it's going to be a 1-to-1 ratio, whether it's +1, -1, +2, -2, and so on. All right. So that's how you determine the formula. The next thing is to determine the name. And the way you do that, if you've got monoatomic ions, so sodium ion, 1 atom, chlorine ion, 1 atom, that's monoatomic. It's a pretty simple system. The cation, the positive ion, retains the name of the metal, and comes first. The anion, the negative ion, adopts the name of the metal, except now it has an IDE suffix. So this is how the element chlorine becomes the ion chloride. And so this is how this gets the name sodium chloride. So let's do another example. Play along at home. I hope you will. So let's talk about the ionic compound that is formed between the elements aluminum and oxygen. Now, both of these are type 1 ions. They adopt usually 1 and only 1 charge, and that charge can be deduced from where they are on the periodic table. Oxygen in that entire column is -2, and aluminum is +3. And in case you're wondering that compound, we don't do this anymore, haven't for several years, but back in the old days when we had shuttle launches every few months, these were accompanied by these huge billowing white clouds coming, and a lot of this was ice crystals from the water that is the exhaust from some of the fuel systems, but a lot of it was this compound that comes from the combustion of the fuel in the solid rocket boosters, the little ones off to the side here. So the first thing you probably want to figure out is figure out what the empirical formula for this compound is. Now, be prepared. You will likely have to write a letter of apology to maybe your 7th grade math teacher. So what would the formula be? Now remember, you want the ratio of these to be such that the charges balance out. Now these are not the same charge. So what ratio so obviously it's not going to be a 1-to-1 ratio. So hit pause, think about it for a sec. Okay. Now, the quick trick for this is you simply can make the charge of one ion the subscript of the other. And that gives us a formula of Al2O3. Now let me show you how that works. And maybe you came up with this on your own. So obviously you don't want 1 to 1 or 2 to 2 or 2 to 3. So basically what you want to find is the lowest charge where these both can cancel out. That happens to be 6. So if you have 2 of the +3 aluminums, that gives you a total positive charge of +6. And if you have 3 of the -2 oxides, that gives you -6. And +6 and -6 cancel out. And this is the smallest set of integers that will cancel out the charges. You will also note that 6 is the least common multiple of 2 and 3. So think back to grade school math and when you were learning about least common multiples, and you were thinking to yourself, when am I ever going to use this? You're going to use it now. So there is actually a place to use it. Now, total charge is 0, so we know we're good. Now, what would we call this? Again, the rule is you go with aluminum, the name of the metal, unchanged, and then the name of the other element with an IDE suffix, so the element oxygen becomes the ion oxide. So this would be called aluminum oxide, and the formula is going to be Al2O3. Now, because both aluminum and oxygen are type 1 ions, they only adopt one charge, you can figure out the formula from the name. You know, aluminum is only going to be +3, oxygen is only going to be -2, so they're going to form in a 2 to 3 ratio, like we've got in our formula here. So, there's a complication. What if it is one of those nasty type 2 ions that can adopt more than one charge? And this dull red powder here is an example of that. This is Fe2O3, commonly known as rust. Now, from this formula, you should be able to tell me what the charge on the iron is. So think about that for a sec. And the key to doing that is the fact that you know what the oxygen is going to be. You know that oxygen is -2. This gives us a total negative charge of -6, which means we have to have a charge of +6. And that implies that, and if there are 2 of them, that would tell you that the iron has to be +3. As opposed to one of the other forms of ions. So one little addition to this naming scheme is that if it is a type 2 ion and you want the name of the compound, not the formula, you have to explicitly give you the charge of that, and it's usually going to be the cation, which is almost always going to be in metal. And the way we depict that charge is we just put it in Roman numerals. So this is iron, and this would be pronounced or spoken as iron 3 oxide. Now, you don't need to say that explicitly if you've got the formula, because you can deduce the charge because you know what oxygen is. And if you've got the empirical formula, you can figure out what the iron is. All right, so iron oxide is not correct here, and you have to be more specific and say there's iron 3 oxide because there are other iron ions. Okay. So while we were on that note, the other iron-oxygen ionic compound is this guy, FeO. So think about it for a sec. Tell me what the charge on that iron ion is and what the name would be. Hit pause, come on back. All right, so this is iron 2 oxide. Hopefully you figured this out. You've got a -2 ion, they're 1 to 1. That tells you the charge on the iron in this compound is +2. So this FeO would be properly referred to with, as a name of iron 2 oxide. All right, let's see how you're doing so far. I have 3 formulas and 3 names. Hit pause, and try to give me the name for the formulas and the formulas for the names. Hopefully that wasn't too painless, or painful, I should say. All right, first one, aluminum chloride. Now remember, if you said aluminum 3 chloride, that technically isn't right because aluminum is a type 1. It forms only positive 3 ions. So the next one, we've got the metal potassium, the element fluorine. That's going to give us potassium fluoride. Oh, and by the way, remember, fluorine, OU is how it's the correct spelling, common mistake. And finally, this guy would be sodium sulfide. Again, none of these should actually have a Roman numeral in it. So what about sodium iodide? Hopefully you got NaI for that. Calcium bromide. So you've got calcium, bromine. Calcium is in the column where they tend to form +2, and bromine is in a column where they tend to form plus or -1 ions. So they're going to react in a 1:2 combine in a 1:2 ratio. So that's going to give us an empirical formula of CaBr2. And finally, lithium oxide. Lithium is in the column where they form +1 ions, oxygen -2. So you're going to need 2 +1 lithiums for every -2 oxygen, giving us a formula of Li2O.